In this screencast, I want to talk about some extensions to the network flow models that we've been looking at. The first one we're going to look at is sometimes referred to as the transshipment problem. But the idea here is that you're going to have multiple sources and multiple sinks, just like we've seen in some of our other examples. But now we're going to have intermediate nodes, which are neither sources nor sinks. And we're also going to allow multiple paths into a source. And in the previous applications that we've done, the simple ones we've done, there's typically only been one edge going into each of the multiple sources. So here the sources are vertex 1, vertex 2, and vertex 5. The sinks are vertex 3, vertex 8, and then 6 is what's known as a transshipment or intermediate vertex. The idea here is that if you look at the sources, they're denoted by a -7. So the numbers are referred to as demands, and if they're positive, that's a sink, and if they're negative, that's a source. The other thing to keep in mind that makes this problem a little different is that it's a satisfaction problem, not an optimization problem. You'll notice that the sum of the source amounts is equal to 21, as is the sum of the sink amounts. And so typically this would model multiple warehouses and multiple retail outlets. And the idea is that you'd want to ship from all the warehouses and get exactly what you need, which is the equivalent of what the warehouses supplied at the retail outlets. This slide is the formal definition. You can look at this. Again, we start out, we've got a directed graph with edge capacities. We've got these demands and supplies. We denote that by D of V. And if D of V is greater than 0, that means it's a demand. In other words, it's going to be a sink in the circuit with what's going to call the circulation. And if D of V is less than 0, that's going to be a supply. So what is a circulation? It's a function that satisfies the following. That satisfies typically the capacity conditions that we've talked about in the other models, and with this additional condition that the amount into a vertex the amount out of the vertex minus the amount into the vertex equals D of V. So if the amount out is less than the amount in, then D of V will be negative. And if the amount out is greater than the amount in, then D of V will be positive. And that's exactly how the vertices were labeled. And that's so that we want our flows now to satisfy that. And the typical problem, as I said before, is does there exist a circulation? In other words, does it satisfy these conservation conditions? And clearly, if you want those conservation conditions to be satisfied, then if you add up all the demands, it has to be the same as if you add up all the sources and take the negation of that, just as we showed was shown in the previous example. So how do we reduce this to max flow? Well, we just label the arc for each V if it's negative. Then we have an arc from the source to that vertex with that capacity. And if it's positive, if there's a demand, then there's an arc into positive demand, then there's an arc into the sink. So this is exactly the same thing that we've been doing, even though we've got some sort of extra wrinkles to the problem. So here's what the final graph looks like, flow graph looks like. Here's our source, here's our new sink, and the edges out of the source are labeled with what the demands were. So this was one of the sources in the graph, and now these through 3 and 8 were the sinks, and their edges to the new super sink are labeled with what their demands were. So now a graph G will have a circulation if and only if this new graph G prime has a max flow of value D. Now D is just the sum of all the edges, capacities of the edges coming out of the super source, which is equal to the sum of all the capacities going into the super sink. And so there's a circulation if and only if the flow saturates all the arcs, leaving S and entering T. In fact, if all the capacities and demands are integers, just as with the standard network flow problem, then there exists a circulation that's integer valued. And again, just as with network flows, the normal simple network flow model, circulation does not exist if and only if there exists some partition, right, at the capacity of that cut, basically, is smaller than the sum of the edges, the capacity of the edges going into the sink, namely capital D. Here's a simple example. Here's our original problem. We have two sources, two sinks, and these are the capacities of the edges and the current amount of flow. We add a new source, we add a new sink, we run the program, say Edmonds Carp, and what do we get? We get these flows where we get 6 coming out and 6 going into the sink, and they're at full capacity, so we know that the problem is solved. Then if we look at the solution, we can see what happens. We get 3 units both to the full capacity to these original source nodes, and then we send from this source, we send 1 extra unit down here, 2 units down to here. That satisfies this demand, and then we also send 2 units across here and 2 units down here because we had 4 over there, and that satisfies that demand. Now this is another extension. It's got demands like it does, so that means we have multiple sources and multiple sinks, but we also have lower bounds on the edges. That's kind of a new wrinkle. So here's the formal definition of that. You have to look at this at your leisure and make sure you understand what it means. So the arc capacities now, same as they always have been, but now we add on each arc a lower bound, LV. And thus, this forces flow to make use of certain edges. That means if an arc has a lower bound on it, an edge has a lower bound, that's the amount of flow, the minimum amount of flow that has to flow along that edge. And now a circulation is a function that satisfies both these new capacity constraints here, where the flow has to be between a lower bound and the total capacity. And then it also has to satisfy these conservation conditions, that the sum of the flows out of a vertex minus the sum of the flows into the vertex equals the demand at the vertex. So again, the problem is, given this graph with vertices, edges, lower bounds, upper bounds, and demands, is there a circulation? So how are we going to model this situation? Well, we have our lower bound and our upper bound on an edge between V and W. And so what we're going to do is we're basically going to enforce this 2, making it across that edge, by upping the demand at V by 2 and upping the supply at W by subtracting 2. We'll do this for all the edges, and notice that when we do this, we have to change the capacity. We have to subtract the lower bound from the upper bound, and this is the capacity that's left, and you can think of this extra 2 units as sort of just flowing through here by magic. So turns out exactly what you'd hope for happens. There exists a circulation in G if and only if there's a circulation in G prime. And the circulation in G is also integer valued. So this is the same example we looked at before, but now we're going to change the problem. We're going to have a lower bound on this edge, and you'll see that that's going to change the answer that we get. So what happens? How do we incorporate this lower bound? Well, just as was on the last slide, the way we do it is we change the demands. This demand becomes minus 1 now. So there's only a supply of 1 here. And now we have a supply of 5 here because effectively we've said we had to ship 2 of the supply down here to satisfy the lower bound. But once we've done that, we've got a little problem because now we've got 5 units here. We're only going to be able to send 2 units over to here to satisfy this demand and only 1 unit to come down and be left to get to the 4. So the amount that's going to be able to flow to the 4 now is only going to be 3. So with a lower bound, you can definitely change the solution of the problem. In this case, there was a solution that satisfied the problem and was a circulation, but now the solution, once you converted it to a network flow problem, you'd find that you're only able to satisfy 3 units out of the 4 units of demand down here. You might think about why that happens. So now I want to look at an example that uses both the extensions we've talked about, namely multiple sources and multiple sinks and lower bounds. And we're going to want to get a circulation. Now this problem you could probably solve without using the formalisms that we've got, but it's a good illustration of how the formalisms get used. So that's what the point here is. So here we want to design a survey, and we're going to ask N1 consumers, about N2 products. So in other words, just think of a company and they've got lots of different products that they sell, and maybe Starbucks or something, and you want to do a survey on how satisfied the consumers are with the different products. But as with most surveys, you don't want them to be, you want them to be relevant to the consumer. So you can only ask a consumer about a product if they own it or have used it. And you don't want the survey to be too long. So you want it to have between C sub I and C sub I prime questions. And you want to make sure that you've got enough questions so that you really learn something about the product. So there's going to be a lower bound P sub j and an upper bound P sub j prime of the number of consumers that you're going to ask about that product. So you want to design a survey that meets these specs if possible. So here's the problem set up. We've got consumers. The arrows represent, do they own the product or have they used the product, whatever is relevant for the particular survey. You've got some number of consumers over here, we'll index them by I, and some number of products over here indexed by J. And then we'll model the problem by creating a network flow model that's going to be a circulation eventually, and we'll have our lower bound and our upper bound on the edges that come from the source and go to the consumers, and we'll have edges that go to the sink, and they'll have their lower bound and their upper bound that reflect the constraint on the number of questions that need to be answered, the number of consumers that need to be surveyed about that product. So now we need to get rid of the lower bounds. So our first step is going to incorporate lower bounds into circulation. So when we look at this, we've got our lower bound is C sub I, so we'll put a supply here in all these target vertices, each consumer, and we'll put the sum of the C sub I here as a demand. So there's going to have to be that amount of flow coming into here. So over on the product side, we've got our P sub I and P sub I primes, and remember that P sub I is the lower bound. So this edge is mislabeled. This should be P sub I prime minus P sub I. And what we get is P sub I demand at the products and a supply at T that's the sum of the P sub I's. So now we've got a circulation and we've removed the lower bounds. And we've changed the capacities of the edges appropriately. And of course, the edges between the consumer and the products are either a 0 flow or a 1 flow. So let's make this a little more concrete to make it easier to understand when we get to the solution. So we're going to have 4 consumers, each one with basically a supply of 2, which is guaranteed by the lower bound. And the products, there are going to be 5 products, and each one of those has a demand of 2, right, which again comes from the lower bound. So we've got 10 units of demand here, so that means for circulation we'll have 10 units of supply here, and over here we've got 8 units of supply, and so we're going to have 8 units of demand here. So now I want to convert this circulation to a network flow, and again we'll go with the concrete numbers. So again, here's our picture. We've got S flowing into each of the customers, and the capacity of these edges is each 3, and over here we have these edges flowing into the sink, and the capacity of each one of these edges is 1, because that's 3 minus 2. And we're going to add this edge in so that we can have a circulation. We've got to be able to, remember, we got to have the flow be able to go around. So we're going to have to be able to send, potentially send what's over here over to here, and we'll just assume that this could be whatever capacity we want. So now what we'll do is we're going to introduce a new super source and a new super sink for this new circulation problem. So notice what we've done is we've started with the original model, converted to a circulation, then we have to convert it to a network flow, okay, and that's what we got to do with these T, S star, and T stars. So now if you put all the appropriate edges in there, and you can see here's a couple of them just for illustration. These green edges here are the edges from the super source now to the customers, and those are each have capacity 2, and there's also an edge from here to T, and that's going to have capacity 10. And again, you got this, same thing from the products. Remember, there's sinks now in the circulation, so they'll all go to the super sink. So now you run the model, and the flows that you get are the numbers in red. So what you can see is that from the super source to each of the customers, you're going to have a flow of 2. But in addition to that, you're going to have this extra flow of 2 down to T. And that flow of 2 is going to come around from T and go over to the S here, and then that can be distributed again, potentially to the customer. So this is another survey question, and we've got 2 units. We can add an additional survey question to 2 of those customers. Now remember, those customers had 2 coming to them flowing from the super source already. So you're going to have basically 8 units of flow here from the super source directly, and then you're going to have another 2 units of flow that come along through T, swing around through S, and then get distributed over the customers. So a simplified version of what's going on is right here. We've got our super source. It's giving 2 units to each possible to each customer. In addition, the 2 extra questions that you need for the products, they go through S. So these edges enforce that you're going to get the 2 units for the lower bounds, and then the extra units that you need get distributed however they'll work through the customers. So if there is a circulation here that satisfies the 10 units of demand, 2 units for each product, then you're going to have these 2 extra units, and you're going to be able to tell which customers where questions are going to be used by whether the flow on here is 0 or 1 on these edges. So that shows how the problem gets solved. And again, now keep in mind that for a much more general problem, you wouldn't be able to reduce it to this sort of simple picture. You'd have to just let the engine proceed. In other words, sort of the process proceed where you first create the circulation, then get rid of the lower bounds, incorporate them into the circulation, and then finally put in a super source and a super sink and reduce the problem to network flow. So I hope this is helpful and gives you at least a brief overview of how you use circulations and lower bounds to solve more complex problems with network flows.